Welcome to the lab for SQL. We're going to have a hands-on and SQL queries that we'll be writing. But before we do that, I thought it'd be a good idea if we had a review of relational algebra. So let's go through a few of the slides from the previous lectures. Here's our schema for the university database. And relational algebra, like SQL, is a language that can query relational database tables to get result sets. And they have a variety of operators. One is the selection operator, denoted with the Greek symbol sigma. And an example of its use is we might want to get the records in the instructor table where the instructors have a salary greater than $85,000. And it's constructed like this. We put the table or tables of interest in parens. Then we have our sigma operator and a predicate or condition, salary greater than or equal to 85,000. And this will return the rows of the input relation or table that satisfy the predicate. Another option is, or another operator is the projection operator, and that's denoted by the capital Pi letter. And that's going to return all the rows of a table, but only the columns that are designated. So, for example, Pi ID, comma salary, parens instructor, is going to return all the instructor rows, but only the ID and salary columns. The natural join operator takes two tables and returns a result set of one table, and it joins the two tables together on common field names so that they records in the left-hand table match appropriate records in the right-hand table. The Cartesian product is where we take all combinations that are possible from the rows in the left table combined with the rows in the right table. We also have set operators such as the union operator, and that takes the result set of one relational expression and merges that with the result set of another relational expression. The format of the select operation or the notation is given here. We have our relation or table in parens, and there can be more than one table. We have our predicate. That's the condition we're using to filter rows from that table and only show the rows that satisfy the predicate. And then the sigma indicates that we're filtering rows and we want to select only certain rows from the table. An example is here at the bottom of the slide. In parens, we have instructor, so we're going to be returning instructor rows. Our predicate is department name equals physics. And we have the sigma operator indicating that we're going to filter rows based on that predicate. So what this relational expression does is returns the rows in the instructor table where instructors are in the physics department. Here's an example with an abstract table. We have a table named R, and it has columns A, B, C, and D. Here's our relational algebra expression that we're going to apply to R. And it's column A has to equal column B, and column D, the value there has to be greater than 5. So let's look at each one of the rows in turn. Here, column A, the value in column A does equal the value in column B. And the value in column D is greater than 5. So we include this record in our result set. With this record, the value in column A does not equal the value in column B. For the third record, the value in column A does equal the value in column B, but the value in column D is less than 5. And finally, the last record in table R, the value in column A does equal the value in column B, and the value in column D is greater than 5, so we include that in our result set. The projection operation has the notation of capital pi, and then a list of attributes or column names, and then the relation or table that we're applying it to. So an example would be to show the ID, name, and salary only, those columns only, of all records in the instructor table. And here's an example of the projection operation. We have our abstract table R. It has columns A, B, C. We apply this projection to R. We only look at columns A and C. So these are columns A and C. But notice we have a duplicate set of rows. Relational algebra will automatically remove duplicates. And so our final result set is indicated here on the right. Just like in SQL, we can do aggregate functions in relational algebra as well. We use the gamma operator or the gamma letter as a notation that we're going to be doing aggregate functions. So in our example here, we have table E, and then we've got a set of functions that we're applying, F1, and F1 is being applied to attribute 1 or column 1, and likewise F2, A2, and so on. The functions can be, let's take an average of that column. Let's find the minimum value in that column. Let's find the maximum value in that column. Let's sum the values in that column, or let's just count the entries in that column. Now, we can do a group by as well. So we can put to the left of the gamma operator, G indicators indicating the fields we want to group on. And so a group by is simply we sort the table by the field indicated or the column indicated in the group by statement, and then we do control breaks on it. We sort it by that column, and then we do control breaks when the value in that column changes. We create a subset, and then we do our aggregation operator on that subset. So here's an example of using an aggregation operator without a group by. We're just doing a sum on all of the records in in table R, column C. So column C, we're just going to sum it up. So 7 plus 7 plus 3 is 17, plus 10 is 27. And so that's what the query optimizer returns to us. Here's an example where we're doing a group by. Notice the syntax, department name, the column that we're grouping by is to the left of the gamma operator. And then we have the function, the aggregation function we're going to apply to the right. And in parens for the aggregation function, we have the column we're going to apply that function to. And then finally at the end, as we have in all of our relational algebra expressions, we have the table we're doing this on. So for department name, we'll take instructor, and sort it by department name, like you see here. Then we establish that we don't do that, the query optimizer does that. Then the query optimizer establishes control breaks. It finds when the value in department name changes, and it groups those into subsets. It then applies the aggregation function to each one of those subsets in turn. And we get the results as you see on the right-hand side. We can also rename the column that we get for applying an aggregation function to give it a name that we can address later on. By default, it's given no name at all. So let's look at a few queries. First, find the names of all instructors in the physics department, along with the course ID of the courses they have, they have taught. So we have two tables, it appears, just reading through the query, instructors and teaches or taught. So we're going to do a join between teaches or instructor and teaches. So one way of doing a join is just manually, we do a cross product between instructor and teaches, and then we find all the rows where instructor ID equals teaches ID. Then we've joined together and we have all of the information in both tables, which we need to answer this query. Then this result set, which is another table, a temporary table, feeds into the next outer select statement. So this select statement is we only want the records where the department name equals physics. And then finally, we pick just the instructor ID and the course ID columns of this next temporary table to give the correct result to the end user. Another approach to doing this is a little more efficient. In this case, what we do is we first filter out the records from instructor where they're in the physics department. So that will drastically reduce the size of our instructor table. We then do the cross product with teaches and do our join criteria manually here with the outer select. And then finally our projection just to pick the instructor ID and course ID columns from that. This is more efficient because it's doing far fewer combinations in our cross product or Cartesian product. Later on, we'll see under query optimization how the query optimizer, the strategies it uses to figure out what is the most efficient way to run a query. And we finish up with our schema diagram for the university database. Okay.